Hello guys, welcome to this video. So I'm doing a video like this after a long time, this whiteboard. So basically I'm in India right now at my parents for this summer holiday after completing my first year of my master's degree in Montpellier University, France, and I do have like a 1 month holiday right now before the second year begins, and that's why I have some not a lot of free time because I still am there are stuff going on my academics and research, but that's why I thought to do a video. And before I begin this video, I would like to give you a heads up. This topic is technical, like way more technical or niche as compared to my previous, if you look at when I began this YouTube channel or my very old videos, I used to do these kind of videos like lectures on whiteboard. But the topics were mostly high school physics or statistical physics, quantum physics. Some of them were a bit technical, but still they were mostly topics that would interest a large number of students or people on YouTube. This, on the other hand, it's a very technical topic, so maybe it would not be relevant to all of my viewers. Just a heads up. But in this video, basically, we'll be discussing the Rouse model, the Rouse model. What is the Rouse model? It's a model of polymer physics basically. So this is something even I learned recently in my master's, and it's very important if you are into biophysics or even like polymer physics, because polymers, what are polymers basically? For those of you who don't know, polymers are like basically, it's a chain of, it's actually a biological, or from a biological or chemical point of view, it's like a chain. For example, it has some chemical units called monomers. That's the way we study it. The DNA is a polymer. There are many biopolymers. Proteins are kind of some proteins are polymers. The DNA, the RNA. So all of these biopolymers, they're polymers. There can also be artificial polymers, which are not biological. But of course, we will not be discussing about those stuff here, and I'm not an expert on those stuff as well. But to study polymer, purely from a physicist's point of view, from a physics point of view, polymers are very interesting, because in physics, when we talk about statistical physics, for example, we talk about a box of gas, right? So gas particles. So, and it's in a way easier to study these kind of systems because all the particles are in a way independent, because they are not connected to one another. It's just a bunch of particles. Now, let's say if you connect these particles in a chain, then basically what you get is a polymer. But here the physics is much more difficult, or I should say much more non-trivial, because the particles or the monomers cannot move independently, they are all connected. So this entire thing is called a polymer, and these individual units are called monomers. So a polymer is a connected chain of monomers. So if you want to study the dynamics of this polymer, it may, at first glance, it may sound like, okay, maybe there is some equation of motion, just like if you have a particle with some mass m and some velocity v, you have an equation of motion which is basically, I'm not sure if this is visible, a velocity v, yeah. So then you have an equation of motion which says that the force, which is the force on this particle, is equals to the mass times the acceleration. So the force is basically dp dt, where p is mv, so I should write m dv dt. So this is basic Newtonian physics. I'm not considering relativity or, here the mass is constant. Force is equals to, so this is what you have, right? The mass times this is the acceleration. This is equal to the force. So if you're applying a force to the body, then this is how it would respond to the force. This is what you have for a free particle, like for a particle of mass m and velocity v. But if you have, let's say, two particles which are connected like this, it's of course it's not as trivial as that, because you can apply a force in this direction, so it would act on this, but it would also act on this because they're connected. So to study these kind of systems, or in general, even when you study statistical physics, we talk a lot about correlations and stuff. Now, this is just a very general, I'm trying to motivate the Rouse model basically before starting the questions, but as I already warned at the beginning of the video, this video is going to be a little bit more technical, and it's not possible for me in a single video to cover all the details. So I'm assuming that you are more or less aware of some basic, even I will be discussing random walk as well. So even if you don't know the technical details of a random walk, that's fine, but I'm assuming you know some basic physics. That's it. I don't have a list of exact prerequisites, but what I want to say is that some parts of the video will be a little bit more technical. That's no reason to stop watching the video if you're actually interested in the topic. Of course, I mean, if you do not get one particular step in the derivation, you can always look it up on the internet. You have ChatGPT for that. You can also comment down below. I will definitely reply if you do comment, but I mean, there are faster ways, quicker ways to get your doubts solved. I'll try to be as comprehensive as possible, I know. So this is the question. This is my writing down an equation that will govern the dynamics, the motion of polymer, basically an equation of motion of polymer. It's not as straightforward as this when you have a single particle moving, or even when you have two particles which are colliding but they are independent particles. The kind of systems you have all studied in high school physics, I think, right, like collisions and stuff. But this is a connected chain. So if I just ask you for a moment to forget all of these polymers and stuff, and just give me a simple example of a very simple physical system, which most of you, in fact I think all of you are familiar with, that slightly, reminds you of this. Not necessarily of a polymer per se, but reminds you of connected things. And I think the answer most of you already know is harmonic oscillators or springs, right? So in fact this is how I have decided, like I have planned to transition to the Rouse model. So for example, you can have, let's say, a body, this kind of, I'm just drawing this diagram just to, because I think many of you guys will be able to relate to this diagram. That's what I mean. It's very familiar. So let's say you have a spring, and then you have a body of mass m attached to the spring, and then you have some rigid support. It can be a wall, it can be, please do not mind the noise because it's the road here and vehicles are passing. I don't want to pause the video when there is some noise, it breaks the flow. So this is the wall, this is the rigid wall. So technically you can think of it as a second body of mass m2. Well, in these kind of problems, like in high school level physics, usually you don't consider the mass of the wall, it's just a fixed support, but I'm just trying to give you the idea. So you have an object with some mass here, and you have another object with some mass here, and they're connected. So and if you keep continuing this, then this is kind of reminds you of a polymer, right? You have another mass here and they're all connected like this. So this is just like a polymer chain. So, and we all know what the equation of a spring is, right? Like the harmonic oscillator. What is the equation of a harmonic oscillator? We all know. And this in fact is kind of a motivation. I don't actually want to claim something I'm not sure of. I do not know historically how did this guy called Rouse, how did he come up with this equation, with this model, whether he was actually motivated by this exact system or something else, I don't know. But this is a clear motivation. At least for me, it's a very good, very clear motivation to go to the Rouse model. This connected springs. So for example, I think when we talk about crystals and stuff, you must have seen this kind of so you have a spring and then you have a lattice. So these are the lattice points and they're all connected by, these are the lattice, whatever, maybe atoms. If you're talking about a crystal, these are the atoms. And then they're all connected by springs. This is a good model. And for that you can actually write down Newton's equation. So if we start with a very simple, for example, this is 1 and then let's say this is 2, okay, and then let's say this is 2 and then let's say this is 3. So and let's say this continues, this is just a one-dimensional lattice or one-dimensional line, whatever you want, whichever term you prefer. So then what would be Newton's equations? Newton's equation is just force equals mass into acceleration. So mass times acceleration is the second order derivative. So these are the things which I am assuming you already know when I said I am assuming you. So these are the prerequisites which most of you probably do anyway. So this is your acceleration, the second order derivative with respect to time of the position. So since here the position can be either this 1, 2 or 3, or in general I am calling it I, where I can be 1, 2, 3 and so on till infinity if it's an infinite. I can continue. So I'm calling it Ri, you can also call it Xi, but this is just a matter of convention, just a matter of notation. So Ri is the position of the ith atom, ith particle, whatever. So for example, this position would be R2, this would be R3, this would be R1. So in general I'm calling it Ri. So here you have Ri as the position. The second order time derivative of that will give you the acceleration multiplied with the mass, and you have the force. So this is your force. So this is one side of the equation. What would be the other side? Well, if you look at it, if let's say if this is Ri, then this would be Ri minus 1 because it's the to the left. So this is R2, this would be R1, and 2 minus 1 is 1, right? The index. And similarly this would be Ri plus 1. So for now I am focusing only on Ri, only on this Ri. So if you focus only on Ri, because that's what you're doing in this equation, you are interested in the question that I'm focusing on Ri, and how does this position Ri change with time? That's what this is telling you. And of course the mass, I'm assuming all of these have the same mass m. You can also complicate it by saying that this has mass m1, this has mass m2 and stuff. But let's start simple, that's always what we do in physics. So this is the thing, and the question you're asking is that if you apply some force, maybe you're pulling it, you're pushing it, whatever, then how does this position Ri change with time? That is what you're asking, right? So this is what, and this is how you want to track that dynamics, that motion. So this Ri is directly connected to Ri plus 1 and Ri minus 1. You also have, let's say, 4 here and blah blah blah, but this one is not directly connected to this or anything beyond this. So to understand what happens to this, you only need to consider Ri plus 1 and Ri minus 1. And if you do, this is a very simple derivation. I think most of you have done it in high school or at least in undergraduate. But again, I'm not assuming that all of you are physics undergraduate. That's why I try to keep this video, at least even if you do not follow each mathematical step, at least you get the idea. So then you actually get this. I'll just. Yeah, I always have a problem with the sign here. I actually prepared some notes as well, because in this video I want to cover some very important scaling laws and derivations of the Rouse model, so it's not possible to, it's good to have a guide. So yeah, this would be your Ri plus 1 plus Ri minus 1 minus 2 Ri, yeah, this is, and some K is your spring constant. How did I write this, by the way? I'm not sure if this is visible. This is the problem actually with that light here, but don't worry, I can just try to. Yeah. So m, yeah, this is very good. Ridt square equals to k Ri plus 1 plus Ri minus 1 minus 2. Now again, I'm not going over this derivation because this is I won't say this is non-trivial, but this is trivial compared to the Rouse model, let's put it that way. But just to give an idea, what is the equation of a spring? You know that force equals minus k, let's say r. So if you have a spring, and if you are applying some force here, you always have a restoring force. This is Hooke's law, restoring force. This is for elastic springs. I mean, there are some assumptions for which this law holds. It's not a very general, it doesn't hold for any kind of system, but yeah, for elasticity, Hooke's law, most of you are familiar with it. I'm not going into the details, but if you apply some force, so by force again it would basically be m d2 r over d t square. Here you have a single body, so that's why I'm calling it r, not calling it ri or something. Then if you pull it this way, the spring will try to go to the other direction. That's why we call it a restoring force, and that's why you have a negative sign. If the force is in the positive direction, the response to the force is in the negative direction. This k is the spring constant. It gives you like the intensity or the strength of this restoring effect, and yeah, it's an r. So this is the general form. But here, let's say you are applying a force in this way. So of course you will have a minus ri. So basically minus k ri. But then for this also you will have something. For this also you will have something because it's all connected. So if you combine like the responses of all these three bodies, because you are focusing on Ri, so you have to take into account Ri minus 1 and Ri plus 1 only. Then you get this basically, where K is a spring constant. Now, again, I think if you are not familiar with this, you should look into this derivation once. It's not very difficult. It just directly comes from this. I sometimes personally get confused with the signs. That's why. But yeah. But now let's say we know this, but we want to model for a polymer. So polymer, usually let's try to look at the biological motivation even. So when you have a cell, you have a fluid in the cell, the cytoplasm and everything, and let's say you have a DNA or whatever, you have some polymers in the cell. So these polymers are in an environment. So it's in a medium which is usually viscous, right? Viscous, of course, even I am in a medium right now, this is air, and even air is viscous. The viscosity of air is much less than the viscosity of water. Again, that depends on whether I'm talking about kinematic viscosity or dynamic viscosity. It's not always, but yeah, you know what I mean. Air is less dense than water. But yeah, so polymers are usually in a viscous medium, surrounding viscous medium. And you know the formula for, like the basic formula for viscosity. If you have a viscous drag, a friction, it's a type of friction actually, because it damps the motion of the object in the medium, whatever the object is, whether it's a particle, whether it's a polymer, whatever it is. So that kind of force, it is proportional to the velocity, it's directly proportional to the velocity. So more the velocity, more the damping effect, more the velocity, stronger the viscous resistance, stronger the viscous drag, right? So when you have a freely falling, let's say, sphere in air, like in some medium with viscosity eta, you have 6 pi eta rv, so it's directly proportional to v, the velocity. Eta is the viscous coefficient or something, and r is the radius of the sphere, 6 pi is a prefactor, it's basically a geometric prefactor which comes from the sphere. But anyway, so in general this kind of force is proportional to the velocity. So for the Rouse model, let me call it, is this xi, or I mean this is the notation I have used in my notes, but I think it's zeta, yeah, I think it's zeta. So this, it doesn't matter, this zeta is just the, what was eta here basically, just the viscous coefficient, the strength of the viscous drag of the medium. So this multiplied by velocity, because this would be proportional to the velocity. So the velocity here is simply dri over dt, because you have a polymer chain like this and with monomers. So this is 1, 2, 3, 4. So I'm calling the index I, and r is the position of the monomers in the polymer. So this would be one side of the equation, and the other side would be, of course, you will have this term. So I'm just writing it here right now. Okay. And this is just, mind you, this is dri dt, this is the velocity. I'm not writing the acceleration here, because here in the Rouse model we are not considering any active force. If you write m in mass into acceleration, that is force, but here you are assuming there is an active force, you are actually pulling or pushing the system, Newton's law. In the Rouse model, we don't assume that somebody is literally pulling or pushing the polymer. That's why we don't have a term like acceleration, we don't have a second order derivative of the position with respect to time. We have a first order derivative of the position with respect to time. This is just the velocity multiplied by the viscous. This is because of the drag or the viscous medium, the viscosity of the medium. And this is of course not an active force. I mean, in the sense nobody is pushing or pulling the polymer. This is the effect of the medium. The polymer is just doing some random motion in the medium. And this is because of the springs, like the connections. Actually, in Rouse model, when you to make the model solvable analytically, because you need in analytics, you need to solve this equation. You need to write an equation. If you're trying to give a model, you need to write an equation that can be solved mathematically. Especially this was done by Rouse in the 1960s or 1970s, like a long time back. There were not Monte Carlo simulations, or these computational techniques were not very developed at that time. So I think he had to rely primarily on making his model solvable, and that's why to get this expression, this assumption, it's a modeling choice basically. The choice to model the monomers as connected by springs, it's basically just an analytical detail. If you want to simulate a polymer using Monte Carlo simulations and stuff, we don't care about the springs, we just say that they're just connected like this. But again, that's a bit technical, that's not really important, because in this video of course I'll be covering the analytics or the scalings and stuff of the Rouse model. It's impossible to show you simulations on this whiteboard, but yeah. So this is where you get that from the spring, and then you add something, okay, maybe I'll write it here, which is the noise, eta I. So what is eta I? Eta I is the noise. Please don't get confused. Eta is, usually some of you may think that eta may link eta subconsciously to the viscosity, but we are using zeta for that, we are using eta for noise. Just a convention, So what is noise? Well, basically if you have a polymer in some medium, and then this is just basically, you can think of it as thermal noise, because in the surrounding medium there will be some temperature. What is temperature? It's basically like a macroscopic quantity in thermodynamics and statistical physics, but it's coming from fluctuations like some ticks, and it's basically if you in classical statistical physics, it's basically the kinetic energy, the law of equipartition and all that. So basically if you're in the medium with some viscosity, the viscosity will have an effect of drag, which is here, and since you are connected to your neighbors like this is this term, and you have also some thermal noise. Why did Rouse add this term to his equation? because this makes it a bit more realistic. In a real scenario, in a polymer in a viscous medium, there is usually noise. It's not a perfectly ideal case that the polymer is exactly fixed and it's responding exactly and only to the viscous thing, and that's it. It's not a clean model, like a clean collection of springs, like a chain of dots, monomers connected by springs. It's not like that. This makes it a bit more realistic. So, and actually this is important because there is a competition between the thermal noise which kicks the polymer. So let's say this is the polymer and this monomer gets a kick due to thermal noise. So it accelerates. I mean, it speeds up. If I inject energy into you, you will get excited, right? If somebody injects energy into me, I will get excited. So this is in a way increasing the velocity. You see, this is the velocity and this is positive. So if I increase the noise, if I increase the magnitude of the noise, the velocity is going up. This is positive and this is increasing, right? But again, this term itself, this viscosity and term, it's kind of, it has the effect of damping. So it's a competition between, let me call it damping or actually viscous medium, whatever, but I mean, you get the idea. So it's a competition between these two terms, and everybody is connected, so you have correlations. The polymer is not independent bunch of particles like a gas. So this is this term. This is the equation of the Rouse model. I know I'm going very slow, but I want to first, I could have started by saying that, okay, today we'll cover the Rouse model and let me just write the equation. This is viscous damping, this is the springs, and this is noise. That's it. Well, that would be a sufficient definition of the equation, but I'm sure that if I introduced it that way, none of you would have understood the philosophy and the way the model is constructed. I wouldn't have understood it when I first learned of this if somebody told me that, if somebody introduced it to me like that. So now you know. And yeah, in general, now I work on these kind of systems. I work on statistical physics, polymer models, and I worked on the Rouse model pretty recently. I published a paper, like not a paper, a pre-printed archive. It's basically, that's very technical, by the way. So if you are really into these kind of things, you can take a look. But otherwise, maybe that's not very relevant for you. There, I studied something a little bit more interesting. So in the Rouse model, we talk about a polymer. But in my model, what I tried to study, and I'm still actively working on that, so maybe there will be future papers and future results, which I will try to, of course, which I will share on my website, on my research page, so those of you who are interested, they can for sure follow. YouTube is not really the best place because this is highly technical. But yeah, in my model, I asked the question, what would happen if I divide a polymer into two segments, let's call it A and let's call it B, and one segment is more active than the other segment. In the original Rouse model, you just have a polymer. You don't have any these kind of assumptions. The entire chain is subject to the equal conditions, noise and these things. And then I did some Monte Carlo simulations, computational simulations. Monte Carlo simulation is also a very important topic. Maybe I should do a future video on this. But again, just to explain the algorithm, logic, mathematics, of course, because this is a whiteboard, this is not a computer. I did a video on Monte Carlo simulations and Ising model, if I remember correctly. Anyway. So yeah, anyway, in that paper I did some Monte Carlo simulations to get some results, and then I built an analytical argument to verify that, and this is very interesting, but it's very preliminary at this stage. So yeah, it's very important. This is very interesting actually. And so just to finish what I started, the reason I mentioned this was that we were talking about the competition between the damping and thermal noise, and this is a very general comment, not specifically about the Rouse model, but in general. When in the physics of complex systems, be it nonlinear dynamics, statistical physics, or when you're studying like this kind of models, competition between two drives. I don't want to use the word forces because it need not always be a literal force, as in somebody is pushing or pulling. But often the competition between two drives, for example, here it was between damping and thermal noise. This is what gives rise to very interesting collective behavior, rich dynamics, interesting phenomena and stuff. So I'll just write the equation of the Rouse model as a reference, and then we will be moving to the lecture. From here, the lecture is going to get a bit more technical, right? Yeah. I plus 1 plus I minus 1 minus 2 I eta I. So this equation only tells you, if there is a polymer in a viscous medium with thermal noise, then how does the monomer I evolves in time, because we are only focusing on Ri. So this is the position of the monomer I. But here's the thing, I is just an index. So if you have a polymer, I could be 1, 2, 3, 4 as you wish. So this equation is general. The same equation holds for I equals 1, I equals 2, I equals 3, and so on and so forth. This equation is technically giving you the the dynamics of the law of let's say the equation of motion in the Rouse framework of one particular representative monomer, but all the monomers are identical. So this is the general equation. It's important to understand like what this equation is. It's not like this is the model, this is the equation of the model, and that's it. No, you have to understand what this equation is and what it is not. Okay. Yeah, okay. So now next, before moving further, I want to discuss random walk very briefly, but this is very important, and I mean important in general, even beyond the Rouse model. So when we talk about a polymer, it's like a chain like this. I'm very poor at drawing polymers anyway. You have a chain like this, and it's evolving, like it's responding to the thermal kicks and to the viscous medium, right? So that means it's evolving. Let's say the polymer was like this, then let's say it stretches out a bit, then again it curves, and then at the same time it moves. Like if this is the box, initially the polymer was here, then it moves here, then it moves here. So it's like moving, exploring the medium, and also maybe sometimes it's curled up, then it's expanding. These kind of things can happen, right? So to model all of this mathematically, and of course the Rouse model is a very simple framework. It's the first framework to start. You have more advanced models for polymers, of course, but this is the place to start. And if you understand the analytical arguments, the scaling of Rouse model, that's extremely important to understand. If you really understand the scaling and analytical argument of Rouse model, the next models are way more technical, but it's an extension of the same concept. It's just to make it more realistic. But yeah, in the Rouse model, we start by assuming that we have a Gaussian polymer. So what do we mean by a Gaussian polymer? Well, the exact reason we call it Gaussian is that you have a Gaussian distribution of the, for example, in the distribution, if you would look at the distribution of the end-to-end distance, then the position, the histogram of the positions of the polymer and stuff like that. I mean, I don't want to go into that, but what is a Gaussian? Basically, you have a Gaussian distribution. You can write it as a probability distribution would be e to the power some r square or something. I don't want to go into that, but the physical picture, the simple picture of like what is a Gaussian polymer, it's very unrealistic, but it means that the polymer chain can intersect itself. So these things are all possible in the Gaussian polymer. Like I'm not just trying to draw it in 3D. I mean, even in 3D, the polymer chain can literally pass through itself, intersect itself. It's basically like a very, I should say, ghost or phantom chain. That's the term often used, which is not very realistic, by the way. Just give me a second. Yeah, I was trying to find if I have something to show you, but maybe this would suffice for. Let's say I have a very small polymer here. So this is a real polymer. It's not a mathematical model. It's a real system. So of course it cannot pass through itself. I mean, it cannot even intersect. If I try to do it like this, I don't know if you can see. If I try to do it like this, then this point is not an intersection. It's one is on top of the other, like this. But if it's in a Gaussian polymer, it's a theoretical framework, hypothetical framework. The polymer can actually pass through itself. That's an assumption. So if I put it a bit more clearly, it simply means that let's say you have a lattice. We usually model this kind of polymers on lattice. I'm drawing a very simple two-dimensional square lattice. So if this is your lattice, that means the monomers can only occupy lattice sides, like these sides. The monomer cannot be here or here, for example. Okay. So let me think. Let me assume that this is my polymer. This is my 1. This is 2. This is 3. This is 4. This is 5. This is 6, 7. This is 8. This is 9. This is 10. This is 11. So basically, I have a chain like this. Of course, a real polymer does not exist on a lattice. It exists on a continuous space. It can be curved and stuff, but to do mathematics, to do simulations, especially Monte Carlo simulations, molecular dynamics, you can do it in continuous space, but that's computationally expensive and it's not as clever. Maybe I am biased because I do statistical physics and Monte Carlo, but Monte Carlo simulation is about asking what happens when the system is already at equilibrium, and it's a bit clever because you kind of do a shortcut. Of course you have all these kinds of approximations on the lattice and stuff, but it makes it's possible to get analytics. But in a real simulation, in a real system, of course a real system is not on a lattice. But this is how we do. So now we have to understand what we call a random walk. Let's say you have a pointer and you ask the point to walk in the lattice. So when I say walk in the lattice, it can jump from here to here, from here to here, from any of the lattice points. But of course on the lattice points, it cannot jump to here or any other arbitrary position. It has to be on the lattice point. But why is it called random? What is the meaning of random? Random means uncorrelated. That's the best way to understand random, especially when we're talking about this kind of models. It simply means uncorrelated. So let's say you ask me to walk on a lattice. Now I can jump either here or there or there. So if it's not a random walk, then maybe I will walk in one particular direction, or maybe I will walk like in a very ordered fashion, which means I have some memory, I have some correlation, or I have some intention that I want to go in that direction. But if it's a fully random walk, I don't have any memory, any intention, any preferred direction. I would just walk, like this. Sometimes I will go straight, then again this, completely randomly. And over a long period of time, it will be like a mess, And when I say no correlation, it means that one step is not correlated with the next step. If I have a memory that I want to go in that direction, then I jump from here to here, then of course I will go here and I will keep doing that. Which means I have a memory of my past step and I have a memory of my destination. If I did not have that memory, I could have bent like this or maybe like this, but I don't do that. But if it's a random walk, then it's very unlikely that a random walk will continue straight for a very long time. It can continue straight for a few steps, but not for a long time. So now let us translate this idea to mathematics. So random walk, yes, this is very interesting. So let's say we have a random walk like this and stuff. So this is the first step. I'm calling it R1. Then R1 is just the position vector. So from this to this. Then you have R2. Then you have R3, R4, R5, R6, R7, and R8. Right. So if I sum over I equals 1 to n. So here n is 8, but n can be like the number of steps in the random walk of Ri. This will give me something. Actually, this will give me something which I call R. So what is this R? This is the sum of all these vectors. So it's basically the sum of R1 plus R2 is this. Then the sum of this plus R3 is this. Sum of this and R4 is this. Sum of this and R5 is this. Sum of this and R6 is this. Sum of this and R7 is this. And sum of this and R8 is this. So it's always the sum from the initial. Of course I could have showed you directly, but I just wanted to show this visually. It's the sum from the initial to the final point. So it's basically the sum of all, the vector sum of all these steps. This is what R is. And since I told you it's a random walk and the steps are not correlated, so this step does not depend on the previous step, and basically every step is independent, which means if you let the walk continue for a long time, the walk will be isotropic. It means it will explore all the directions equally. If you let it continue for a long time, there will be no preferred direction, like it will keep moving straight, then it's not a random walk. That's why we can say that the average, the mean of R is 0. If the mean is 0, it means that simply over a long period of time some vectors are this, and ultimately they cancel because they are scattered in all directions. Otherwise they would not cancel if it's not a random. This is one of the characteristics of a random walk. So the mean of R is 0. And the next thing is Ri dot Rj. So the dot product of Ri and Rj, and the mean of that is okay. So in the random walk, this is one step, this is the next step, this is the third step. So for simplicity, if you are on a lattice, we are assuming that all these steps have a fixed length, which is a. So this is a in magnitude, this is a. So these lengths are a. So then this would be a squared delta ij. So this is the Kronecker delta. Okay. So what does this mean, by the way? What does this mean? It means that this is the, let's say this is your ith step and the next step is your jth step. So this is Ri and this is Rj. So the dot product. Don't try to think of this as like a orthogonal or like a dot product in that sense, but it simply means that this step, that no step is correlated except if it's the own step. I mean, if you're talking about Ri dot Ri, so basically you're talking about the same step, the dot product with itself, then of course it would be a squared. Why a squared? Because this length is a, and again you are considering the same, so it would also be a, so a times a would be a squared. But if it's Ri times Rj, where I is not equal to j, like you're talking about two different steps, then they are not correlated. Of course, both the steps magnitude is a, the magnitude of the step length is a, but you are talking about the mean. So you are talking about the mean of two steps which are not correlated. So for the mean you need to take observations, you need to take measurements for a very large number of times. And since they are not correlated, it would give you 0. So combining these two statements, you can write that, you can write this basically, I'm not sure if that is visible. So combining these two statements, you can write that, Ri dot Rj is equals to a squared delta ij, Kronecker delta. So what is this delta ij? If I is equal to j, then this is delta ij is equals to 1, which means that you're talking about the same step. So Ri dot Ri because I is equal to j, and then it would simply be a squared because this is 1. And if I is not equal to j, then delta ij is 0. I mean, that is the definition of the Kronecker delta. So then if this is 0, then this entire thing is 0, and that's what it means to say that no two steps are correlated if they're different steps. Well, now that we know this, and we also defined R, what was the definition of I think you can maybe write it here. R was summation I Ri, right? So if I have Ri dot Rj, it would be Ri would be, what would be Ri? No, I think if I just a second. Okay, yeah, that's what I was thinking. Before introducing this, it would be important to talk about MSD, which is mean squared displacement. So what is the mean squared displacement? Okay, so let's go back to the random walk. Let's see what the random walk and displacement. So you are here, and after a certain amount of time you reach here. So this is your displacement. Now, since the random walk, since I told you that the mean of R is 0 and this is this thing, which means that over a long period of time the random walk will explore all the directions. There will be no preferred direction, and because of that, since the mean of R is 0, because of that, the mean displacement will always be 0. This is what I mean by displacement. It doesn't give you any useful information because I mean it will always be 0. It's a random walk. But if you talk about the mean squared displacement, it will be an important observable which will not be 0. Because, for example, you go here, you go here, you go here, you go here. So first this is 1, 2, then from here you go to 3, then you come back to 4, and then you come back to 1. So you start from 1 and you come back to 1. So what is your displacement? The net, the overall displacement from the starting point to the ending point, it is 0. But what is your mean squared displacement? Mean squared displacement, it means first this is your displacement, let's call it A1, let's call it A2, let's call it A3, let's call it A4. So the mean displacement would be just the sum of the displacement divided by the total number of displacement, like the total number of values. That is the mean, right? So it would be A1 plus A2 plus A3 plus A4 divided by 4, and that is 0. Why 0? Because A1 is in this direction and A3 is in the opposite direction. So A1 and A3 cancels because A3 is basically minus A1, and similarly A4, this is this and this is this. So A4 is minus A2. So A1 plus A2 minus A1 minus A2 by 4 is 0, right? Very simple. But if I ask you to tell me what is the mean squared displacement, okay, so mean squared displacement. So first you square the displacement, then you take the mean. So you would have A1 squared plus A2 squared plus A3 squared plus A4 squared divided by 4. Now this is not 0 because even if A3 is minus A1, but A3 squared would still be plus A1, like A1 squared, right? Because if you're squaring something, then even if it's minus, you're squaring it. So that's why it's important to talk about the MSD, the mean squared displacement. But then what would be the MSD of a random walk? So this is the displacement R, you square it, so displacement square, and then you take the mean. So you take the mean. So this is the MSD of a random walk, R squared and the mean. So this would be what? R dot R, because that is basically what R squared is. And what would be R dot R? Well, we know that R is summation I Ri. So this is summation I Ri dot summation J Rj, because we cannot use the same index for two. Like this is just the way we are writing a product, dot product. So R dot R, now R is summation I Ri, or like basically for the second R we are using a different index. Now of course the summation we can bring it, okay, I still have some spacing. So the summation we can bring it out, so summation I, summation J, because this is a mean and the summation we can bring it out, right? Inside the mean or outside the mean, it's still the same summation. In the mean, so then in the mean we would have Ri dot Rj. And we know that Ri dot Rj, the mean, that is a squared delta ij. So we have summation I summation j a squared delta ij. Now delta ij is always 0 when I is not equal to j. So and this is a double summation, right? So for all such values when I is not equal to j, this contribution is 0. We can ignore that. The only contribution will be when I is equal to j, when this thing would be 1. And when if we have I equal to j, then saying that summation I is the same as saying just summation I. So then we would have just the same as saying summation I. So then we would have summation I a squared. Now, so if we have summation, actually the summation runs from 1 to n because if the random walk has n steps. So if you have summation I equals 1 to n a squared, then actually you would have a squared times n. Because a is a constant, so basically the a squared will be outside the summation, and then you have summation I equals 1 to n and then 1, because a squared means a squared multiplied by 1. So if you have summation I equals 1 to n of 1, then you have 1 plus 1 plus 1 up to n, so it's just n, so then you have a squared n. And this is a very important result in random walk statistics, which is, I mean, if you are familiar with this field, you already know this is a very trivial result to even that case, but since this is YouTube, I wanted to discuss this result for the and like the full derivation actually for the general audience, because this is really, and I mean, I find the derivation beautiful actually, even if the result is trivial. It appears trivial to us who work in the field, but actually it's a very important result. So which means the mean square displacement of a random walk is a squared n, where n is the length of the walk, like the number of steps, and a is the length of each step. So translating this to the language of polymers, the mean square displacement of the polymer is equal to the distance between two consecutive monomers, the same thing, the step length, because the polymer is also basically can be modeled as a random walk, and n, the length of the polymer, the number of, also you can think of it as the number of monomers, right? So you have 3 monomers, then the number of monomers is 3, and the length of the polymer is 2 actually. So it's a bit, if you think n is the number of monomers, then the length of the monomer will be n minus 1, because let's say that you take 1 step, you take 2 steps, you take 3 steps. So the number of steps is 1, 2, 3. But the number of points is 1, 2, 3, 4. So, but it doesn't really matter. It's just a matter of convention. But yeah, something to be cautious about. So this is the result. Okay, and here we are assuming that the polymer is a Gaussian polymer, because for example, in an actual random walk, actually you are allowed to come back here and then go like this and then like this, again come back here, again come back here. So these overlaps are allowed. That's why I said the polymer can literally pass through itself. Because if you do not allow these overlaps, then you cannot really say like all these things about a random walk. You cannot say this, because for example, if you say that the polymer has done this and then it cannot come back here because this site is already occupied, that is what we actually call self-avoiding walk. It's called self-avoiding walk. Self-avoiding walk, or SAW. So SAW or self-avoiding walk is basically more realistic. Of course, a real polymer or real anything cannot pass through itself, but that is not random, because the equation, these results slightly change. They have to be modified if you talk about self-avoiding walks. Why? Because if this side is already occupied, so if you say that no, the polymer cannot come back here, then actually there is some correlation. That means the polymer has some memory. It has to remember that I already have occupied this side, so I have to take some other route, but I cannot come back here. But that means you cannot say that all these steps are completely uncoordinated, all these things that I told you, all these results, you cannot really say that for a self-avoiding one. So that means for this result we have assumed we're talking about a Gaussian polymer. Right, now let's talk about the scaling laws in the Rouse model, which is very important and also very interesting. Once you get the feel of it, is very interesting, but I mean I think that's more the responsibility of the teacher, especially if you're learning it for the first time. So I mean, it's on me if you don't. I mean I'll try my best actually, but trust me, if you really get the feel of it, it's really interesting and it's great. I mean, okay, so basically what happens in the Rouse model is that I would just like to discuss something else before we go to the scaling laws, because this will be relevant, this will be important. So let's say we have a polymer like this, and all of these are the monomers. And in the Rouse model, you have this thermal noise, right? You have a thermal kick. So consider any monomer in random. For example, let's pick this one, and let's say this faces like this, feels a random thermal kick. So if I feel some force or some random kick, whatever it is, some noise, and I'm connected to two monomers, and those monomers are in turn connected to their neighbors, then my response to this force will propagate. I mean, suppose if I jump like this and I'm connected to people, then they will also feel the disturbance. They will also slightly jump, and this will propagate, right? But it will take time to propagate. For example, if I feel this force now, instantaneously this monomer at the end will not feel anything. First, my neighbors will feel it. Then after some time, this will feel it. So, you see what I mean? Now, there is something very important in physics which I assume you already know, but I'll just discuss it very briefly. It's not possible to cover everything like I already told you. But it's called the diffusion. Diffusion means transfer of anything. It can be transfer of momentum. In hydrodynamics, you have transfer of momentum, diffusion, all of this stuff. Not just hydrodynamics, I mean diffusion can be transfer of anything. It can be transfer of momentum, transfer of energy, transfer of information, or transfer of even like matter, like particles. When particles are diffusing, for example, you have like two gas A, like gas particles, and gas B, and you remove the partition, the gas diffuses. So those are diffusion, right? But diffusion is not always necessarily about gas particles or like real matter. It can also be more abstract, like diffusion of information. So here, let's say this feels the kick or whatever, this disturbance, and the disturbance will propagate between, like propagate across the monomers. I'm not saying it's propagate across the space. Of course, to reach this monomer from this, you have to move like this. But here I'm talking about the diffusion in terms of I. Diffusion in I, when I is the monomer index. I is 1, 2, 3 and so on, like the monomer index. This is a very crucial idea, by the way. Usually when we talk about diffusion, we talk about diffusion in space, like the gas particles are mixing in real space. So then we would say diffusion in X, Y, Z or something. If it's one dimension, then maybe diffusion in X. But here I'm talking about diffusion in I, which is a monomer index. It's a bit abstract, but the same physics. So the diffusion equation is written like this. Now again, I cannot derive this right now, but I mean this is the basic form of the diffusion equation. So this is dr, since we are talking about diffusion in I, this is dri over dt. So it's a first order derivative in time and a second order derivative in space, and this is the diffusion coefficient d. So d squared ri over dt, sorry, di squared. So actually it's dx squared usually in space, but since here it's a diffusion in I, it would be di squared. So this is the diffusion equation, right? Well, I mean, if I slightly write this equation with the Rouse model in mind, then instead of writing the diffusion coefficient directly, this would be the viscous coefficient here, because this is the velocity and this was the form of the Rouse equation, right? And in the left hand side we had noise. So for now I am ignoring the noise, so forget the noise for now. And we had the forces from the spring, like I mean basically this term. So this was actually the force from the spring. So this was a force. Force means it would be a second order. Force is mass times acceleration. So it's a second order derivative in position, right? So something like this. I mean, so that's what we have. And you have the k here, of course. So this is just writing it in terms of the Rouse model. Well, I mean, if I'm actually being honest, then this r also depends on time. So I should write this partial derivatives, not just to be super rigorous, Why does r depend on? Well, I mean, it takes time. So for example, when time t equals to t1, I mean, just after I feel the disturbance, maybe only 3 monomers have had time to respond to the disturbance, me and my immediate neighbors. Then after some time, when t equals t1 plus delta t, let's say, then let's say the disturbance has propagated a bit further. So 5 monomers, me, my nearest neighbors and the next neighbors have had time to respond, and then it spreads. Which means you see that this is actually a function of time. So I can write it like this, n as a function of time. But okay, I should maybe use small n. So this n is not this n. This is a fixed constant. This is the total number of monomers you have, the total length of the chain, of the polymer chain. But the small n is simply the number of monomers which have had time to respond to some local disturbance. And this grows with time. So it's a function of time, because as time moves, as time passes, the disturbance propagates across more and more number of monomers. So this small n also grows with time. So this small n is not a constant. This is a function of time. Okay, so now actually I can just, now you have k here. So I can just divide both sides by zeta and write k over zeta. And I can define a new constant d, which is basically in this case k over zeta. And this would be my diffusion coefficient. This is the general form of a diffusion equation. Not necessarily only about Rouse model, okay? And so once you have this equation, what next? So for any diffusion equation, we also have, where should I write it? Basically, you just remember this result. This will be important. I'm writing it here shortly. The mean square displacement of a random work is this, a squared over n. And then I'm rubbing this. Maybe I can also rub this because you have got the idea. And now for any diffusion equation, you have, here the diffusion is in I by the way, here it's not in x or any other variable. So you would have the mean square displacement of this variable. So when here I wrote r square, or you could also write it x squared, you could also have written x squared, but here it's I in terms of I. So this is a general kind of result. This is proportional to, actually this is proportional to dt, where d is the diffusion coefficient and t is time. So it's linear in time and it's proportional to, I mean it's very simple to understand, right? So this is the mean square displacement. So with time the mean square displacement grows, like you are diffusing. So when we just start to diffuse after a very short amount of time, when t is small, maybe actually this is actually technically dt, how much the time gap. For a small time gap, you have diffused, but you have not had enough time to move a far distance. So your mean square displacement is small. As time grows, this also grows. So it's linear. I mean, why it's linear? Of course, it comes from the equation, but this is the result. And it's proportional to d also, because d is the diffusion coefficient, but it's kind of, you can think of it like a velocity term. It's not really, I mean, I'm talking about like dimensionally, but it's not velocity, of course. But I mean, this is displacement and this is time. So displacement divided by time is your velocity, right? So you can think of it like a velocity. It's not exactly velocity in the usual sense. But the more the diffusion coefficient, the faster the object diffuses. But why is it not exactly velocity? Because velocity has a particular direction. Like velocity in this direction is not the same as velocity in this direction. But diffusion, when we talk about diffusion, we are interested in asking, how quickly the information or the gas particles or the energy or the momentum, whatever it is, how quickly that spreads in every direction. We are not interested in like one particular direction. That's why we talk about the mean square displacement, because if we talk about only the mean displacement, I already discussed, then it would cancel. It may cancel, right? So then you have this result here. Delta I square is proportional to dt. I'm just writing t for the time, but technically it's a time interval, so don't get confused. These are the things where you have to be, I mean, it's good to be a bit careful, of course, because this doesn't change the mathematical result, but it enormously matters for the conceptual understanding, right? So I mean, okay, you can see this right here. So if delta I square is like this, I'm just talking about scaling laws right now. So I'm not, this is not an exact equality. So if I write an equal sign, then maybe there can be some prefactor, or maybe let me call it c, where c is a constant prefactor, which depends on the system you're studying, depends on the topology, the geometry, the dimension, blah blah blah. So this is the exact equation, but we cannot and we do not need to determine c to get the basic physics of the system. So that's why we are writing delta I square. This symbol means it scales as dt. So this is just the scaling behavior. We're not talking about the exact equation, exact prefactor, everything. And we also know that, okay, so this is the first equation, which means delta I would be scale as square root of dt. So d is a constant. We are not really interested in d now, we are more interested in how it changes with time. So this would be scale as t to the power half. So because this means d to the power half, t to the power half, but this is a constant, so it doesn't change the scaling. So delta I, which means I is the monomer index here, it's diffusion in I told you, this scales as t to the power half. Well, I mean, delta I would also, this would actually be proportional to n of t actually, right? Because I told you, n is the number of monomers that have had time to respond to a local disturbance. And with time, the number of monomers that respond will grow, because of course with time the disturbance will propagate. That's why this is a function of time small n. So I think this delta I is a bit confusing. So I can directly write that small n t scales as t to the power half, right? We don't need all of this anymore. And so now it's time to combine these two results. So this is also the number of monomers n. So if we consider that, we can write it like this, nt. It's important to understand why. This capital N and this small n are not the same thing. As I already told you, the capital N is fixed and it's the total length of the chain. But this formula is not about, like, this is a general formula which says that if you have a random walk of steps n, then the mean square displacement of that random walk will be a squared times n, where a is the length, its step length. So whatever the value of n, this formula will hold for a random walk. And if n grows with time, like if I write it like this, if n is a function of time, then also this formula will hold, right? This formula is not for a fixed n. I mean, of course, this result is for a fixed n, but it holds for any value of n. So if n grows with time, then this would also be a function of time, of course. Like I'm not writing this, but this would also be a function of time. But yeah, so we can say that because we are not looking at the entire chain, but we are looking at the part of the chain that is responding to a local disturbance, thermal kick or whatever, coming from the noise term. If you think, we can think of it like that. Now again, we are talking about the scaling only. So forget the constant a square. We are talking about the scaling only. So r square, the mean of r square scales as this, and again this in turn scales as t to the power half. So I can rub this and replace this with t to the power half. And again, this mean is also, I mean, it's just a mean, but the dimension of this is the square of some distance, r squared. So if this scales as this, then if I want to look at r only, sorry, I think it would be, I think it's better for me to stick to the lecture notes. I was moving far ahead, but I mean, not really, this is actually relevant, but okay. So this is the square of, this is the mean, so this is also a mean, but this is the square of the velocity of the displacement. So if this scales as t to the power half, then if we take the square root on both sides, just to look at the scaling again, this is not an equation, this is a scaling, then this r, only the mean displacement would scale as t to the power half, so t to the power 1 over 4. This is important, okay? Okay, I'm still keeping this result because I think we will be needing it even now. And okay, I actually want to derive the crossover. I think we can do it from here itself, though I followed a slightly different route. Apparently, I think I followed a slightly different route in my lecture notes. Just a second, guys. Yes. No, I mean, doesn't matter. I think we can do it from here itself. So, come here. So, from here we can, I'm just, the point is to get to the result using some scaling, and it's like this. So, this is equal to a squared n, so it scales as n, which means again if I look at r, it would scale as n to the power half. Now, it's important to understand what we are saying here. Here by n we talk about the full length of the chain. So, when I say this, I am assuming that, going back to the language of a local disturbance, if I use this capital fixed n, the total length of the chain, I am assuming that the disturbance has propagated through the entire chain. So now this no longer needs to be a function of time, because if the disturbance has propagated through the entire chain, there is, even if time passes, there is no further place to go for this disturbance. It has already propagated in the entire chain. So this is something, and we also have this. So both of these are the same quantity, but this is important. They are telling you different. They are describing different events, different situations. Here we are saying that the disturbance has already reached the entire chain. That's why we are using capital N. Here we have not strictly assumed that, because here, if you remember, we have used small n t. So here the disturbance need not have reached the entire chain. But even if these two are equal, but if we equate this, then we are assuming, we are asking the question of crossover time. It's very important conceptually to understand this. Of course, you can equate this and get the answer in a second. This is not a very difficult calculation. The algebra is simple, but the concept, crossover. Why crossover time? Because this gives you the time, like basically the scaling law, when you are not assuming that the disturbance has spread through the entire chain. But here you are assuming that the disturbance has spread through the entire chain. So if we equate them, then you will get an estimate for the time, and that will be a crossover time. That will give you an estimate, just an order of magnitude, a scaling estimate, but a very useful estimate. Estimate of when these disturbances or these correlations kind of cancel, because if it has spread throughout and the chain has become fully independent, then the correlations have cancelled. Otherwise, it's spreading, so there are some local correlations, stuff like that. So you'll get that value. So if you just simply equate that t to the power 1/4 and scales as n to the half, then you can raise both sides to the power of 4. Because you want the time, right? So you raise both sides to the power of 4. So to the power 4 to the power 4. T to the power 1 over 4 to the power 4 is just t, and this is the crossover time. So we denote it by tau c. or whatever you prefer, and that would be n to the power, well, n to the power 4 by 2, so n squared. Now this is the important result. So we already have derived one scaling relation, right? So this seems like a very simple, cute equation, but I mean, to come here, you see it's not very, the concepts are not actually trivial, you know. So what does this mean? This means that, let's say this is time, and let's say this is, okay, now this is very important, so I should draw it properly. Actually, you can verify this if you know Monte Carlo simulations. You can verify this using simulations, and that would be a good exercise if you're interested in these kind of things. But this is, let's say, your MSD, which is the mean square displacement. So basically it's r squared in our notation, and this is, let's say, time. Of course, if you do Monte Carlo simulation, this time is not the real physical time, but again, let's not go into the technicalities of Monte Carlo right now. So this is time, t. So there is a particular crossover time, tau c, which scales as n squared. So it's basically equal to n squared, but it's not exactly equal to n squared. There can be a prefactor. Like I said, it depends on whether you're in 2 dimension or 3 dimension, the type of system, some details which we're not considering. The usual scaling, the order of magnitude scaling is n squared of the crossover time. So what happens before and after the crossover time? So before the crossover time, the mean square displacement of this polymer, according to the Rouse model, grows subdiffusively like this, and after this it grows diffusively. So this slope, this slope is actually 1. So this slope is 1. That's what we mean by diffusive, because if you have a slope 1, so what is the diffusion equation basically? Like I told you. So the MSD scales as the diffusion coefficient multiplied by time. So it is linear in time. So this is the mean square displacement and this is the time. So the slope is MSD divided by time. This is the slope of this, and that would be, excuse me. Yeah, I think this is a log plot. Yeah, I'm sorry. This is a log plot. So the MSD usually scales as, again, I'm not considering the constant because it's a prefactor, it's a constant. The diffusion coefficient is a constant. So for diffusion, the mean square displacement scales linearly in time, which means the slope means the y-axis by the x-axis, which is MSD divided by time, is 1. The slope would be 1, right? This is what I mean. Log plot actually, yeah, because if you plot it in log plot, then it will actually get the slope. Just a second. Yeah, so basically MSD is t to the power 1, that's what I mean. So if you take the log of both sides, then you have log of MSD is equals to 1 times log of t, so divided by log of t. So basically log plot would be 1. Anyway, log plot, because it's usually easier to plot it like that, because the time scales and stuff, it's usually in the order of 10 to the power something and stuff. So here the slope is 1 and here the slope is half. Why the slope is half here? Because if you remember, I forgot, but I erased it, but just now we derived, you can just rewind the video and watch. Just now we derived that it scales as, this what we're calling n of t, like not the full chain length, but the number of monomers that has had time to respond to the local disturbance. It scales as t to the power half. That's why the slope is half, because this is time, so it's t to the power half. So here, before the crossover time, for times shorter than the crossover time, you have this, which means not all the monomers have had time yet to respond to the disturbance, but after that it's diffusive. So everyone has responded. This is what I mean. And here, when I say it's diffusive, it's actually very important, because it means that the chain, the polymer chain, it diffuses freely. So let's say you have the polymer in a box. Okay, you cannot see that. Let's say you have the polymer in the box. So subdiffusive means it diffuses very slowly, like very slowly. But if you have if you're in a diffusive regime, it diffuses like this very fast, almost as if it's a collective particle. So in this regime, you can think of it as like an effective picture would be the entire polymer is like a single particle which is moving like collectively. Of course, the polymer is not a single particle; it's a collection of monomers and chain. I told you already, but it moves collectively. But here you have correlation. Some part of the polymer is pulling back, somebody is pushing, like pulling forward, and there is this kind of correlation. So it's not that's why it moves, it diffuses, but very slowly, because you have all these effects. Right, let's say you try to move forward, but some parts of you are trying to pull you backward, then the diffusion will be slower. That's what I mean. That's why this is called subdiffusive, and this is called diffusive regime. Right? Okay. And there are actually something to discuss here as well. This is a bit more technical, which is perhaps not very much required for this video, but I'll just briefly mention this, especially some more interested viewer is watching. Like, this is the MST time, the same plot which I just erased, by the way. So yeah, it's like this and then it's like this, and the order, I mean the time at which this happens. For example, it can be at 10 to the 10 square. So if you have a polymer of length 10, then this will be around of the order of 10 square, because this time, the crossover time is it's n squared, of the order of n squared, right? Now this is the crossover time. Now what I'm trying to say is that, okay, this is time and this is tau c, the crossover time. Okay, so what I'm trying to say is that here actually for very short times, if you I mean what we observe is that for very short times, this mean square displacement versus time, this is actually diffusive. It's actually like this. The slope is 1. Then it is subdiffusive, and then finally it like this is the joint when the polymer diffuses as a collective particle. It's diffusive. So why this is number one question. Number two is that you can have something like this which we call plateau. Now this is not really a physics of the Rouse model itself. This is you can say this is a finite size effect, edge effect, because if you are doing the simulations in a lattice, of course you have to do the simulation in a finite lattice. You cannot do a simulation in an infinite lattice, of course. So let's say you have I'm not drawing the lattice, but let's say you have a finite box like this, and you have a polymer which is like a pretty long polymer, long related to the size of the box, related to the volume of the box. Then of course as the polymer diffuses, there is a high probability that it will bounce off the walls, and it will be confined in the box. It cannot go outside the box. So if you have a very large box and a very small polymer, then it has enough space to diffuse. So I mean, given you do it for a time when it has not reached the boundaries, then it will not observe this. But if you observe these kind of things in simulations, it's usually an edge effect. I just told, of course none of you are doing simulations right now of this, I guess, but I told this just to give you an idea of how these things are very important. And why this? Because at very short times, I mean, again I cannot go into the technicalities, but to give you a simple layman level explanation, in very short times, like when the chain has not yet started diffusing, like at time t equals 0, just starting to, the dynamics is just starting. You can think of it like that, a mental picture. Because usually you do this in simulations. A real polymer in a cell or in any other, like a real polymer, of course it doesn't have a concept of, okay, let me start diffusing now. It's always diffusing, it's always interacting with its environments and everything. But when you do a simulation, you have to define a time and you have to let the system evolve starting from some time. So for very short times, the polymer still has not had enough time to register that I am connected to my neighbors. So if you don't get registered that you are connected, then you're basically a free particle. So that's why it's diffusing freely. You observe this in simulations. But then once you register that, oh no, I'm connected to particles, okay, somebody's pulling me this way, somebody's pulling me that way, I'm facing some kicks, like some thermal kicks, and this information, this disturbance is propagating and it's taking time, then you slow down and you become subdiffusive. And once you have reached the crossover time, you become diffusive. That's the picture. Okay. So this is like the most, this is probably the most important feature of the Rouse model, this crossover time. The last thing that I would like to discuss is that in this video is the diffusion, the system size dependence of the diffusion coefficient. And before that, I mean not really before that, but together, because discussing this would also mean discussing. Okay, I can actually, since we talked a lot about diffusion, and diffusion is really important in physics. So before I end this video by discussing what I told, like the dependence of system size on the diffusion coefficient. Before that, I would like to show you like a kind of like a small simple derivation of this, because I told you that so this was your mean square displacement. I told you that the mean square displacement scales as dt, where d is the diffusion coefficient and t is the time. Now, and this is a very right now I'm talking about diffusion in general, not only in Rouse model. For any random walk, it has to be random walk. Like I told you, you cannot say that it's but yeah, actually no, this is for the diffusion. So if we use this result, that the mean square displacement is a squared n, it grows linear like this, then you are assuming that it's a random walk, it's not a self-averting walk. You can have intersection, like the polymer or whatever the system, the walk can pass through itself. But this is a very general statement because it's about diffusion. Here you don't have any kind of like, it can be about self-averting, about random, about Gaussian polymer, whatever. But the mean square displacement grows with time and it's also proportional to the diffusion coefficient. It's a very general statement. And I would like to show you like a derivation of this, like a simple derivation. It's very, very important. So let me write the diffusion equation first of all. Let me write the diffusion equation. Okay, so I'm writing it in general right now. So let's say delta P delta T is equal to the diffusion coefficient times the second order derivative in space. So right now since this is the most intuitive picture, I'm talking about diffusion in space, and this is in one dimension. As you can see, it's in one dimension. You could have used, instead of this, you could have written the Laplacian operator del square del x square plus del square del y square plus del square del z square. But of course, right now I'm interested in just to give you this derivation. I mean, of course, if I show you the derivation for one dimension, it easily translates to more than one dimension. So let's keep it simple. And this is the most intuitive picture. By x, I mean the diffusion is happening in one dimension. So this is my x, so it's in one dimension. And diffusion means you don't care about the direction, it will happen both ways. So it's spreading. So it's in one dimension, you can spread only either to the left or to the right. And what is P? Well, P is basically, you can think of it as like the probability, like not really the probability, but yeah, it's kind of like the probability that you will find the particle in some place x plus d, because you are using x plus dx. Usually, the usual definition, because this is it's in a way you can think of it like the probability density. P is a function of both x and t, right? So, and this is the diffusion equation. This is spreading in space, and that's why it's a square, because diffusion, spreading, you don't care about one particular direction. It's mean, that's why like we talk about quantities like mean square displacement and not mean displacement. This is the diffusion coefficient, and this is the usual diffusion equation. Just keep it in mind. This is equation 1. Okay, you cannot see the 1, right? Okay. This is equation 1. Okay, now what is the mean square displacement? The mean square displacement is the mean of, so here we are in one dimension x, so I will not use this notation r, instead I will use x. So this is x squared and the mean of that. So in continuous space you have to use integration instead of summation. So this will be integral minus infinity to plus infinity x squared, and then the probability distribution px comma t dx. So this is your, for mean you take the integration on that, and this is your square because it's the mean squared, and this is your mean square displacement, right? Now you take the time derivative ddt of the mean square displacement, right? You see what I'm doing? I'm just taking the time derivative of this equation. This is dx, okay? Dx. I think you can make it right. Okay. So this is the time derivative of x squared, and then it would be simply ddt of integration. I'm not writing the limits minus infinity to plus infinity time and again. X squared p is a function of both x and t dx. Now again here you can actually swap. It's not always true, but in this case you can swap this operator, this derivative operator and this integral operator, because the derivative is a time derivative, the integral is a space derivative. And so this would be integral x squared. You can write del p del t dx. I'm not writing p x comma t again, but yeah, it's a partial derivative in principle, because p is a function of both x and t. So you can write like this, right? Now what is this? This in place of del p del t, I can replace like this. I can replace this, right? So I'll just okay. So here, just a reminder, here we have the time derivative of the mean square displacement x squared. So this means ddt of x squared would be integration x squared. In place of del p del t we have d. Now d is a constant, right? So I can write it here, d, and then we have the second order derivative in space of this thing, dx, right? Sorry, x squared, yeah. So this is what we have. Now it's very simple. So now let's just forget the d, and let's just focus on this particular integral. Okay, actually it will take some space in the whiteboard, so I'll just write this equation once again in the top. I'm removing the Rouse equation by I think. Yeah. So this is the equation we should remember. Ddt of x squared is equal to d times integration x squared. Del square p del x square dx. And right now we are focusing on this squared box, like this integration, right? Okay. So of course we will use integration by parts. It's very obvious here. So if you have this dx. So first, I'm not writing the. I think you all know the rule that if you have a product like uv and integration with respect to x, where u is ux and v is also vx, then you have You choose the first function and the second function using the Eilert rule. Then you have u integration v dx minus integration the derivative of u, so du dx, and then again the integration of v dx, and then the dx. This is the product rule, right? So we will be applying the same rule here twice. So first of course this x square is the first function, here would be the first function, this would be the second function, so it would be x square. Now integration is also with respect to x and this derivative is also with respect to x, so you have a second derivative and you have integration. So integration and derivative are the reverse operators, so the second derivative will become first derivative if you take the integration, so this will be delta p delta x, and the limits will still be from minus to plus infinity, minus the second term minus, first you have the derivative with respect to x of the first function, so ddx of x squared would be 2x, and then you have the again the integration of this, so this would again be delta p delta x, and you have the full integration of this, right? Now this is like a very physical, like it's a very reasonable boundary conditions which we always invoke in these types of problems. So as x goes to infinity, plus or minus infinity, p goes to 0, because of course p is the probability of finding. So let's say start from it and you diffuse, of course you're spreading, you're diffusing, but if you reach actually minus infinity or plus infinity, of course you don't expect to find a particle there. I mean that's the like the end, or infinity is not an end, you know what I mean, but that's a very reasonable boundary condition. You cannot reach infinity in finite time, right? So if you put the limits here, x when x is plus or minus infinity, and then if p is 0, and then of course if you would also need this condition that the derivative of p would also be 0, because dp dx is just the velocity of p. So if you cannot reach there, I mean at that limit your velocity will also have to be 0, just for the sake of continuity. So then basically if you put these limits here, the first term vanishes, goes to 0, and you are left with minus 2 is a constant, minus 2, and then integration x del p del x dx. Now for this portion we will again use the product rule. It's the same structure, x squared and then double derivative, then x and a single derivative with respect to x. So this is minus 2 and I'm using a third bracket. So again x is the first function here. So it would be x, and integral with respect to dx of del p del x would just be p, right? And then the limits minus infinity to plus infinity. Then of course you can see even now that this will be 0, because here you're putting so basically you have p as a function of x and the limits are minus infinity to plus infinity. So p of infinity plus or minus is 0, and similarly del p of plus minus infinity del x is also 0. That's what we used in the previous result. So then you have the first term is 0, and the second term would be minus. Well, you have the derivative of x with respect to x, and that will be 1, and then you have the integral 1, and then again the integral of this, so this will be p. So 1 times p is p, so you have integral of p dx minus infinity to infinity. Now p is the probability distribution, and of course if you have so that means it has to be normalized. If it's a probability distribution, it's normalized, and if you have a normalized distribution, normalized in one dimensional space x, and you are integrating through this entire space from minus infinity to plus infinity dx, so this has to be 1. So then you have minus 2 minus 1, so it is just plus 2. So this entire integrated box evaluates to plus 2. Okay. So then you have basically ddt of the mean square displacement is 2d. So if you take the integral again, so 2d is a constant, right? So if you take the integral, it will be x square, the mean square displacement is equal to 2d t plus some constant usually, but yeah, so basically this from the scaling point of view, this is the equation. So since we were in one dimension, so in one dimension you can have two directions to spread, basically that's why you have the two, I mean if you're in two dimensions, basically x and y would be independent, so you would have something like this, and then you basically would have 4 here if you're in 2 dimensions. If you're in 3 dimensions you would have 6, but this is the prefactor, not very important. But you see the relation that the mean square displacement in general, it scales as dt. That's what I wanted to mainly show you. Finally, it's important to understand when we talk about the diffusion of the Rouse polymer, the Gaussian Rouse polymer. So see, I mean, for example, from the point of view of just a small comment before I show you the final result. The final derivation is very interesting, by the way. But just a small comment. When you do simulations, for example, this is the mathematical definition of MSD. But in simulations, how to define MSD? This is your polymer chain. You take any one monomer at random, like usually you take it from the bulk. These are the edge monomers, and somewhere in the middle is the bulk monomer. You take a representative monomer and you track it. So you run Monte Carlo simulations to update the polymer, update the moves on the random walk on the lattice to model the polymer, and you take you take measurements. That's what I mean to say. So you take measurements, and how do you define the mean square displacement in such a situation? It would be, first of all, it's a mean. So here in simulation it means you take the average across many different runs, and like basically ensemble average many different trials, and then you can also you also have to take a time average, of course. And then it would be the position r at some time t minus the position of some monomer. You have chosen a monomer I, so ri at time t minus ri at time 0. This will give you the displacement, because when time t was 0, you were here, you were in this position, and when time t was t, some later time, you are in this position. So subtract them, you get the displacement. You square it and you take the mean. So, and you can take measurements of this in simulations. But the point is, how do you extract it? This is very important for many physical systems, by the way, not just the Rouse model. How do you extract the diffusion coefficient? You can have measurements of MSD from your simulations. So let's say you know what MSD is. But then let's say you're doing simulations on a 2-dimensional square lattice. So on 2D lattice, this MSD would be 4 times diffusion coefficient times t. Actually t would be your, if I'm strictly speaking in terms of simulation, t would be your lag time. So basically it's not always 0 to t. You define a time difference. So for example, it would be, I should write the MSD as RT plus delta t, RI t plus delta t minus RI t. You understand? And then make a time average. So, because for example, you define a lag time of, let's say, I don't know, maybe 5 seconds. Again, in simulations, it's not literal physical time like seconds or minutes, but you know what I mean. So then you have, let's say you start from time equal to 0 to, you look at what happens when time is 0 to 5. You don't stop there. You take a measurement and you note it. Then you look at what happens from 1 to 6, because still the difference is 5. So you look at all such delta t difference as t evolves. Then you look at what happens from 2 to 7, then from 3 to 8 and so on, and you record all of this and you take their average, and you take their absolute value, then you square it and you take the mean, and then you get the mean square displacement. So you know MST, you know delta t, and if you are in 2D, for example, this would be 4, otherwise it would be 6, if in 1D it would be 2 as we derived just now. So then when you actually plot this from your simulations, MSD over t, the slope of this plot, what would be the slope? The slope would be MSD divided by delta t, right? So this plot is actually delta t, to be more precise. So that would be from this equation 4 times dCm. Why I write cm? Because here actually it's usually we talk about the diffusion coefficient of the center of mass. I will come to that, because that is the last part I have discussed. I already told you. So basically, from this simulation you get this, and you can of course fit the curve to get a slope. And once you know the slope, you divide the slope by 4, because your slope is equal to 4 times the diffusion coefficient. So divide the slope by 4, and then like this you can extract the value of the diffusion coefficient. It's a very useful technique. Okay, but now finally what I want to discuss is this result. So we discussed this central result in Rouse model, that the crossover time scales as n squared, and below the crossover times for time less than tc, the mean square displacement is like it scales as t to the power half, and then it becomes diffusive for t greater than tc. We discussed this thing, right? And the next important result, very important result in the Rouse model, is that the diffusion of the center of mass scales as 1 over n, or if you prefer n to the power minus 1, same thing. Now what is, first of all, the physics of it, and then I will be deriving this result. We already have enough mathematical machinery, like whatever we discussed, if we have followed it to that point, then this derivation would not be very difficult, but it's still interesting and somewhat new. Like it's not a, you will need some new concepts which I have not yet covered. But this is a very important result. Why? Because what is this telling you basically? Forget the details, for the technicalities. So n is the length of the polymer. So let's say you have a small chain here and you have a large chain here. So which will diffuse faster from this equation? What do you think? If n is large, then this diffusion coefficient is smaller because it's inversely proportional to n, which means this will be slow and this will be fast. Fast diffusion, slow diffusion. Why? Well, it may appear counterintuitive to you in the first glance because, well, it's a small chain, so it means that it will be more correlated. Because statistically, we expect the larger the chain is, the larger the number of steps in the random walk. We expect like it's not correlated, it's completely independent, so it will diffuse very fast. But here it's kind of in the opposite, that it's a large chain, slow diffusion. Important point is just, we will be deriving this of course, but just to give you a very rough physical intuition, physical kind of picture of this, what's happening. If you have a very small chain, even if the chain will be very strongly correlated, since you have only a small number, everybody's more or less correlated, stuff like that. But look at what happens here. You have the crossover time. So if n is very small for a small chain, very quickly you reach the diffusive regime. And once you reach the diffusive regime, you have a very small chain. So it's almost like everyone is it's a collective motion is easier. If you have a large chain, then well, somebody is there dangling like this, some part is there. So it's very difficult to organize it into a single collective motion. It takes more time. That's why you see you have this. So if n is large, n square, the time taken scales as square of that. So small chain diffuses faster. So now it kind of makes sense, I think. But the exact derivation of this is very interesting. So for that we need to define something called the center of mass. So what is the center of mass? So let's say if I have a polymer like this, the center of, so for the polymer the mass is concentrated only across it's a one-dimensional chain. It can curve, it can fold in 2D, in 3D, but it's a one-dimensional chain basically, right? But so if it's curved like this, its center of mass it could be somewhere here, I don't know. So if it's like this, center of mass could be here. If it's straight, the center of mass could be here. So basically the formula for the center of mass is, so RCM. RCM is the position of the center of mass, RCM, and this is the mean of this displacement, that Ri minus, it's a mean square displacement, but the mean square displacement, what displacement? Ri minus, I think no, that was the radius of gyration. I'm sorry, never mind. The center of mass is simply the mean, the average, so let me write it in full. It's the 1 over n, because if you have n monomers, or the length of the polymer is n, or in other words, if you have n steps in your random walk, so it is 1 over n equals 1 to n Ri. That's it. I think I wrote the definition correctly, but yes, this is correct. Or this is simply the average, right? So this is the mean of Ri. That's it. This is not a mean square displacement or anything. It's just the mean of the displacement. So, well, it's not really the displacement, by the way. In the sense that the way to think of it is, I think. So this is your R1, this is your R2, R3, R4, R6, R5, R7, R9, R8, whatever. So if you take their mean and you get some mean, could be here, for example, RCM, then this is the position of the center of mass, because the masses are in the monomers, right? That is what we assume. Of course, we have springs and stuff, and in a real polymer, it's not that simple that you have some concentrated monomers and you have nothing in between, like you have very small. It's not like that. But in this kind of models, the masses are in the monomers, and you have these connections, springs or whatever. In the analytical model, we model them as springs. But yeah, so this is how we define center of mass. Just to give you the physical, once you understand this, then the derivation is just some steps of algebra, right? But this is important to understand. So we take the average of all the position vectors, Yeah, okay. So basically, what is the center of mass? It's an observable, because we always cannot talk about Ri. We always cannot talk about each position, the position of each monomer individually, and if we talk about only one particular monomer, if we pick one monomer arbitrarily, that's okay. That's how we do the MSD, for example. We can do the monomer MSD. But sometimes we want an observable which takes the average of all the positions and then gives me an average of the center of mass position. That's what we mean. Because here the masses are only in the R's, like I told you. So then we have this, and now I think so this is what we want to derive. So I will write it in the top left corner. DCM is proportional to 1 over n. I think you can see this. So this is where we want to reach, and this is the last result I will discuss in this video. It's already very long. The first, and then we are given this, the center of mass is 1 over n, summation I equals 1 to n. I will be writing from this point forward, I will be writing summation I, so we will understand I mean summation I equals 1 to n, Ri. And we are also given the Rouse equation, the original Rouse equation. I'm just writing it here once again. I mean, I have to write it for this derivation anyway. So R is basically a vector, even center of mass is also a vector. Yeah. Is equals to K Ri plus 1 plus Ri minus 1 minus 2 Ri. Even noise is a very interesting topic. I try to discuss that. You have different types of noise like Gaussian white noise, annealed noise, wedged noise. This is very important. I mean, actually, what type of noise we talk. Here you can think of it as like some random kicks in random directions. But noise is itself a very interesting topic to discuss. But yeah, so now let me take the summation on both sides. So let me take on both sides summation I, and let me divide both sides by n. So if I divide both sides by n, I also have to multiply both sides by n, right? So in the left, I am multiplying by n and dividing by n, and I am taking summation I. We forget the n on the right hand side. I am just multiplying and dividing the left hand side by n. I can do that. For that, I don't need to multiply n in the right hand side. It's the same thing. If you multiply n here, then you can bring the n here by division, right? Summation I zeta d ri over dt. I'm not giving the vector sign over r every time just to save some time, but you know that it's a vector. And this is zeta, yeah. And in the right, you have summation I k ri plus 1 plus ri minus 1 plus 2 ri minus 2 ri plus summation I eta. Okay, first of all, this term will be 0. Why? Because it's in this model, like everybody is connected to everybody else like this. You know what I mean, right? I'm just showing this. So if you sum this over I, which means we're summing over every possible, every possible monomer. So ultimately, like all the opposite interactions will cancel out. You see what I mean? This interaction is pairwise. So if you sum this over I equals 1 to n, so ultimately you will have, for example, you will have a pair like I to j. And for every such pair, you will also have j to I, the exact same j to I, so they will cancel out. And so in the end, everyone cancels everyone out. You understand what I'm saying? You're summing from I equals 1 to n, you're summing over all the monomers. And you have this, it's just connected, the pairwise interaction, so it will cancel. Or I mean, even if you want a simple physical picture, I mean, if you have this kind of spring models and you are summing all the interactions, then it cancels because that's the way it is. Because you have no, I mean, this is coming from the viscosity of the medium, and this is coming from the noise. But I mean, this is like you don't have any other external force in the system. Everyone is connected, and everyone feels these connections locally. But if you sum it over, nothing remains. So this is 0. And now look at this. So just look at this 1 over n summation I. Okay. So here we have this thing. So n, zeta is a constant. I'm writing zeta like this, and then we have ddt here. So ddt is a derivative with respect to time. The summation is a summation over the monomer index, not exactly space, but yeah, over the index of monomer. So we can swap. So let me bring the derivative outside. So n zeta ddt of what we have here inside the derivative is 1 over n. We have this n here. Summation I ri. So what is this? You see, this is the center of mass. So we can write that this is the n times zeta times the time derivative of the center of mass. So this is basically the velocity of the center of mass will be equal to, this is 0, and okay, so this is the next important thing. So we have summation I zeta. So this is noise. So this is noise, and this is actually for this I think I get confused here because I will use the lecture notes for this part. So this is a random thermal noise, and each thermal kick, like I was talking about the kicks which are coming from this noise term, they are independent. So basically what I mean to say is that this noise is uncorrelated. How the noise will affect which monomer at this point, at this step, doesn't depend or is in any way correlated to how it will affect in the next or the previous step. That's what I mean. So it means that of course this is, since it's a noise, it will have like a distribution, for example, and then you will have a variance, and then you will have a mean, which is usually 0, and then you have a normal distribution kind of. I cannot discuss this here, it's already a long video, longer than expected, but I mean that's the way I operate anyway. I rarely am able to keep my videos short. I'm sorry for that, but anyway, this. But yeah, this video, I think, to my defense, I think the topics were discussed were really important, and I tried to discuss it. I hope I tried to discuss it in a very comprehensive manner. So of course, it will take time. So yeah. So each such random noise has a variance, standard deviation, variance, whichever term you prefer. Variance is the square of standard deviation. Let's say sigma squared. And since the noise, each of the state is independent, if I sum over all this, actually I have to sum over this. I have to sum over the variance. What is the definition of the variance? Is this summation I eta I minus the mean of summation I eta I. Okay, and square of this. So this is the definition. Well, this is the mean, and this is the mean of the noise, and this is the mean of the mean, and then you have the square of that, and you have. So this is how you define the one way to define what is the mean of squared minus the square of mean, something like that. So it comes from here actually. So this would be proportional to. You can see this expression right here. So this would be proportional to sigma squared and n sigma squared. Why? Because here, since the noise is uncorrelated, as I told you, that means the variance in this step is sigma squared. The next step would also be sigma squared. It's not uncorrelated. It doesn't depend on anything. It will just add. So if it's independent, it will add. The variances will add up. And if you keep adding n times, so you will get n sigma squared. That's how you have this. Now, the mean of the noise, this term basically will be 0 because it's the mean of the sum over all the noise. So when I told you summation I means summation I equals 1 to n. So the noise is completely random and it's n steps, the total number of steps is n, and you are summing it over and then you're taking the mean. Of course it will be 0 because it's random. So this is 0, and what you have here remaining is that summation I eta I squared. You have a squared here, so this is not 0 of course. So you have this remaining, and this is proportional to n sigma squared. So again, let's come back to scaling. So if you just look at the scaling, then what would be this summation I eta I, just the scaling. You can also write the mean, but I'm just interested in the scaling. So this would be proportional to this. This would scale as you're taking the square root basically. So it would be proportional to sigma times n to the power half, or if you prefer square root of n. And this is the term we have here, right? So we know the scaling at least. Oh, so what did I write? This is sigma times square root of n right here. Remember this. So right now this we have, and here this term is 0, and for this term, since this is a scaling, we cannot use an equality sign, but we can write like this, that this is sigma times square root of n, right? Okay, so this is basically the velocity of the center of mass, VCM, because this is the position by time is velocity, right? So VCM, the velocity of the center of mass, is proportional to sigma times square root of n divided by this zeta times n. Of course, physically it makes sense because this tells you velocity means how fast the center of mass will move. So basically, how fast it will diffuse in a way. And this tells you, well, okay, so this is the noise, and I told you it's a competition between the noise and the viscosity. So more the noise, the more the thermal kicks to the monomers, and the faster it will move because the noise is pushing and telling you move, diffuse faster. So that's why the velocity is of the center of mass is directly proportional to the noise. So as the noise grows, this also grows. But this is inversely proportional to the viscosity, of course, because this is zeta is more the viscous coefficient, more the drag in the surrounding medium. So you find it more and more difficult to move in a very highly viscous medium. So as this increases, this velocity decreases. Physically, this equation makes sense, right? The next thing is that we will take another conceptual leap, if I may put it that way, and we say that, and we say that we will be needing this equation, so I'm not writing this. We say that, okay, so VCM is the velocity, and we define some time, again it's not really crossover, you can call it a correlation time, so I'm calling it tau c, or let's say TC, no, because it's kind of the same thing, but because when you talk about tau c, it's proportional to n square, it's also in a way like the time it takes for it's technically the relaxation time also, we call it the relaxation time also, This one would be then the slowest relaxation time. The time it takes for the entire chain to get uncoordinated, and after that you have the collective diffusive regime, where the chain drifts or diffuses collectively as a whole. So velocity times time would be your displacement, right? RCM. We can write an equation like this. Let me just check if I am proceeding in the right direction. Yeah, I mean in principle, yeah. So, I mean, of course, we can write an equation like this: velocity times time is displacement. But it's important to understand what this time actually is. So, this is well, it's in principle a correlation time. I think there is a slight mistake in my notes here. It cannot be. Yeah, I mean anyway, so I mean actually what I mean by this is this VCM depends on this. So this is a constant, this is a constant, this is also a constant. This depends on the noise, this comes from the noise, right? So this is a correlation time, yeah, but this is I should write it NC. This is a noise correlation time. That was a slight mistake in my notes. But anyway, so this correlation time tells you like after what time the noise will be completely uncorrelated, and only then you can write an equation like this, because to get this we actually assumed that this was n sigma square and all that, like this we had a summation of the noise term and it scales as, right? So this is the noise correlation time, and this gives you so I mean if you write an equation like this, you know, in terms of the noise correlation time, and after this the center of mass diffusion, then here you can use this equation VCM, because here you have actually used the same thing, like, you know, at time scales greater than this you can actually use this value, because here you have assumed that noise is not correlated. Okay, but first of all we are interested, since we talk about diffusion, we are interested in the mean square displacement, not just the displacement. So you take the square of that and you take the mean, so then it would be simply VCM squared over T NC squared. It was stupid to rub this, but thankfully I think I remember there were n zeta and then it was sigma n square root of n. So this was your VCM, right? Yeah, okay. So then this would be VCM squared, so it would be sigma squared, square root of n squared is just n, over n squared zeta squared, over n squared zeta squared times T n c squared. You get it? So n and this n would cancel. And this thing we already know from diffusion equation. We have discussed this many times in this very video. That this mean square displacement of. So here we are talking about the displacement of the center of mass. So this would be proportional to, you know, the diffusion coefficient of the center of mass times the time, some kind of correlation time. You know, I'm not sure if I can write the noise correlation here, but yeah, I think I can, because when we talk about in the frame of the center of mass, you just have the noise and you have this. You don't have anything else. So the correlation would be in terms of the noise, because this term is anyway zero in this frame of reference, right? So I already told you why the mean square displacement, like the MSD, scales as diffusion coefficient times time. So here we have the mean square displacement of the center of mass, so the diffusion coefficient of the center of mass and the corresponding time scale. This is a scaling. You can in principle have a constant prefactor here, let's say some constant C1, but you don't care about that. So let's say here you have a constant C1 just to be extremely rigorous, and now you already have your result if you see. So you have T and C here because it's a squared, and you just cancel the square with here, so you then have C1 DCM equals T and C. Sigma squared, sigma is a constant, it's a variance of the noise, but it's a constant in itself, divided by n, and zeta is also a constant. So you can write the C1 here. So C1 is a constant, this is a constant, this is a constant, this is the time you have. But in general, if you look at the scaling, DCM scales as, so you have an n here, so it scales as 1 over n. This is a very beautiful derivation. This is where we wanted to reach, by the way. So yeah, that's also something I wanted to tell you. And yeah, I think I should stop here because there are a few other points I wanted to discuss. In principle, I could have, but I think I should stop here because it's a very long video, and I'm also feeling a bit. I mean, I need to drink some tea or coffee or something. I mean, I'm feeling a bit. I've spoken for a long time, and I am doing this whiteboard kind of lectures after a long time. If you guys have any feedback or about anything basically this topic, or like if you would like me to cover some other topic, of course if it's within my knowledge, it's possible for me to cover, you can, of course. But yeah, I hope you enjoy the video. If you have any comments, anything, please feel free to write a comment. And thank you for watching. And yeah, that's it. We should have. I mean, I could have covered a few more like self-avoiding that would have been more realistic, bit more technical as well, but more interesting. Like when we extend to self-avoiding work, we have these universal constants, critical exponents, stuff like that. It's very important, by the way. But yeah, it's not possible to do all of that in a single video. And today, I mean, in this video, what we discussed was mostly the Gaussian polymer, which is where to start basically. And of course, this model is very simple, very in a way unrealistic, because of course real polymers cannot pass through themselves. But this gives you a very good baseline to test all of the scaling laws. And much of these laws that I showed you, like this scaling laws, this dynamics, it's a very general feature. It holds even if you extend to self-avoiding works. You can have some modifications in the critical exponents, stuff like that, but the basic the physics actually the physics here is very non-trivial. And if you understood the derivation, the scaling laws, I mean that would be great. I mean, to be frank, it's not really possible to understand it in one sitting. It took me a lot of time, and I tried to teach it in as comprehensive as possible. And also I discussed a lot of stuff which is not usually discussed at the level of when the Rouse model is introduced. I don't think the Rouse model is technically a part of a general master's, but I mean if you're specializing in polymer physics and stuff, then of course you would know what a random walk is and what a diffusion equation is. But I still, since it's YouTube, and also I like to start from the scratch and cover make the video as comprehensive as possible. I could have said that, yeah, so we know this is the diffusion equation, we know this is this, and but that doesn't feel very good to me. I mean, you can go to ChatGPT, and ChatGPT can show you these derivations in a few seconds. But I wanted to give you the feel. I mean, I could have written the equation of Rouse, but I wanted to give you a feel that this is the competition between the noise, the thermal kicks, the thermal noise, and this viscous, and the idea of with this equation. That's why I started with very simple, with a box of gas as compared to some connected springs and then polymers and stuff. Anyway, I hope you enjoyed the video, and thank you for watching.